Hello friends, I hope you are doing well. So up till now, in network theory, what we have seen that we were analyzing the circuits based on the voltage sources which have a direct values which does not change with respect to time. But but from today's videos onward, we will be analyzing the circuits in which the voltage sources, the current sources, they will have varying voltages, varying current sources, meaning they will have an AC current or voltage sources which change with respect to time. They will have an angle, they will have a phase, they will have a frequency. Based on that, the analyzation will be we will analyze the circuit. So without wasting any time, let's get started with the AC analysis of the circuits. Okay, but before moving forward, what you need to know that you should know the basics of AC analysis. So with that keeping in mind, so let's start with the very basic thing, that is a sine wave, a sinusoidal waveform. Up till now, in DC circuits, what we have studied that the every element has a fixed predictable values. Suppose a voltage source have a value of 10 volt, it will be remain 10 volt throughout the circuit. But everything's not predictable, or it does not it's remain unchanged. In AC analysis, in AC circuits, those values, the same value, those values, they change momentarily. After some moment, they change back and forth, a positive, negative at any given point in the circuit. Okay, so how we can know that what suppose in the circuit there is a node, what kind of value will be there in suppose if that circuit is an AC circuit. So what we do if I have a practically what we do is we connect two nodes at that point. One is a positive node and one is a negative, and we see a waveform. Based on that, we can say that in there this kind of voltage or current is flowing. That waveform is called an AC waveform. There will be some shapes. Either it will be a sine wave or a square wave, or it can be a rectangular wave or any other different type of wave. So the simplest waveform that we can recognize is the sinusoidal or sine waveform. Well, let's talk about this sine waveform. So first of all, what kind of sine wave it is? What is a sine wave actually? The question is, what is a sine wave? A sine wave is a natural description of oscillation. Natural description of oscillation. Meaning, if I want to give an example, suppose you are riding a bicycle, you pedal the bicycles. That pedaling gives us a smooth oscillation, a repetitive smooth oscillations. Okay, that pedaling goes up, down, up, down, up, down, up, down, up, down. That oscillation, we can, if I want to represent that oscillation, it will be somewhat like this. If on a graph I show like this, it will be something like this, up, down. This is a sine wave. This is a sinusoidal waveform. This is a sine wave. Here, if we talk about in terms of current, the current changes or alternates between two polarities with respect to some parameters. If the parameters basically we take here time, with respect to time. Okay, so this is a waveform, a sine waveform. To understand this waveform, there are some basic terminologies. The first one is a time period. Time period T. What is a time period? The time taken, if I write here, the time taken to complete one cycle. Now, what is a cycle? This is a cycle. This waveform, you can say, to complete one cycle, this from 0 to some point, positive and negative, from travel from positive then negative, this is a cycle. This, to complete one cycle, is called a time period. And the reciprocal of time period is known as frequency, F, and it's measured in hertz. So we can write here F equal to 1 by T, and this from here to here, it's called time period T. This is the wondrous frequency, or you can say the number of time cycles completed. That how many number of cycles can be completed in a frequency, in one time period? How many? Okay. Basically, the time. This is a fundamental time period. After that, it gets repeated. This is a fundamental time period from 0 to, let's say, it's called T. This is a fundamental time period. Okay. Now, secondly, if we move further, suppose this is 0. This will have some value. It's called a peak. This will have some value. Suppose it has a value 2. Then this will also have some value. Suppose let's say its value is -2. Then what will be the value from here till here? What will the value? We call it as a peak to peak value. Peak to peak value, or VPE. If this is a value, this peak value is a 2, and this peak value is -2, then its value is 4 VPP. Okay. Next, this much is clear. I hope this much is clear. Next, what would happen if I double the frequency or double the time period? Let's see about that. Let's erase from here. Okay. If I double the frequency, let's erase the above one. We don't need it. Okay. If I double the frequency, this will happen. Okay. This, the red one, is when frequency is doubled. It will become faster. The number of cycles in a given period will be more. Okay. Now, what would happen if the time period gets doubled? The time period gets doubled, then it will be like this. This is when time period is doubled. Okay. The time taken to complete one cycle it gets doubled. If it's the original is t, initial is t, then when the time period is doubled, it will get 2t. It will take 2t time period to complete 1 cycle. I hope this much is clear to you. Next we move, say, what would happen if this amplitude gets doubled or it gets halved? Let's see that. I hope you have written all this or taken screenshot. If I have, suppose, this is t and this is my initial, this is my the initial, the original sine wave. What would happen? And here its value of 2. This is minus 2. What would happen if amplitude gets doubled or gets halved? This is the question. First, let's see what would happen if it gets doubled. Fine, obviously, the amplitude will get double. If its value 2, it will get 4. This, but the origin point will remain the same. This will remain the same. This will be the waveform. This is minus 4. It will get 8. Okay. This when amplitude gets doubled. Okay. Now, what would happen if it gets half? Simply it gets half. It will, first one is 2. Initial was 2. It will be 1. This minus 1. This is when amplitude gets halved. Same case for when it gets tripled or divided, gets 3 times, half by 3 times, reduced by 3 times. Same thing. Okay. So this is what, just like what would happen if the waveform gets double frequency or we have double time period. Same thing. Now, moving further, it is also possible if we talk about a DC voltage, or we can say that we can add a DC offset well. What is a DC offset? Basically, it's a DC voltage, a DC number, DC voltage. What would happen? Let's see. Suppose I just erase this one. Let's erase this one. Now, if here also 2 cases. If I have a positive DC offset, first, and second is if I have a negative DC offset value. What would happen? If I have a positive DC value, then it's 0. It starts from 0. Then suppose I add a 20% or 10%, let's say 10% DC offset value, positive 10%. Then if it's 0, what will 10%? Around somewhat here. It will start from here. Okay, this is a positive DC offset, okay, by 10%. Okay. Secondly, if we add a negative, then here suppose I have negative 10%, then it will be start from here, somewhat here. It will be go like this. This is a negative DC offset by minus 10%. I hope this much is clear to you. Okay, you can take the screenshot of this. Now, till now we have seen that what do you mean by amplitude, what will happen if double the amplitude, half the amplitude, what is frequency, what is time period, what would happen if there is a DC voltage added. Next is, it is also what would happen if sometimes what will happen, the waveform, there is a shifting in waveform, there is a shift in the waveform. We call it that there is a term that is called as a phase shift. So if, let's draw this waveform again. Okay, now taking the same waveform, this is the waveform. Okay, this is the waveform, this is 0. Now we have two type of phase shift. Phase shift, one is a leading, other one is a lagging. Leading means that the waveform it starts from earlier, it takes a lead. Okay, now for example, this is the initial waveform. If I take if I have to draw a leading waveform, then the waveform will not start from 0, it will start from somewhat from back side. Okay, like this. This is a leading waveform. Okay, by any angle, by suppose it's by either by theta value can be anything, 45 degree, 90 degree, 270 degree, anything. And then we have a lagging. So lagging will be from here. This is a lagging by any value of theta. Okay, so lag means they start from late. The waveform starts from late. Like I have to do some work. I have to do some work, but I lag it. Or you can say the best as an alarm clock. You just lag by some 5 minutes or 10 minutes. That thing, or you say snooze. So the alarm will be delayed by 5 minutes or 10 minutes. The same thing is leading and lagging. So I hope you understood this all terminologies. With that terminologies keeping in mind, there is a general form of to represent a sine wave. Vt voltage. Okay, so VDC, this is a DC offset, plus Vp, this is the peak value sine 2 pi ft, this is a frequency, plus theta, this is a phase shift value. Okay, so a sine wave can be represented mathematically in this format. So I hope you understood how we can write. Suppose if I give an example, this is 0, this is 1, this value will be 3. Okay, so this is your homework. What is VT? This thing. How we can write it? Simplest. Okay. Just write in the comment section. Okay. So I hope you understood our today's video. This is just the beginning of the AC analysis. See you in the next video. Till then, I have a request for all the new as well as the old subscribers to like this video if you liked this video. And for new subscribers, please subscribe the channel if you're new to this video, and press the bell icon so that you won't miss any future notifications. See you guys in the next video. Till then, thank you very much.